All right, so today we're taking a look at the area of a triangle and one example of a story problem. We've been talking about law of sines, and so now we can use law of sines in these story problems, but the challenge is drawing the diagram, and that's really what we're focusing on in that example. Here we have three identical equations just to represent whether we have a known angle at A or B or C in each of these cases. And since we don't have a height, what we're really recognizing here is that it's 1/2 times the base times the height. This is a way to find the height of your triangle, right? So C times sine of A, that's the height, if you will. So instead of finding the height as a separate step, we're just putting it all in here, and there's the formula of your triangle. So notice what they're giving us is the B and the C. The B and the C are the sides on either side of angle A. So in other words, we have to have a side angle side pattern, and then the formula will work. Here's just another variation of that if you happen to know angle B. And in that case, the sides are A and C on either side for that side angle side pattern to work. And sure enough, there's the A and the C. So that's what they're saying with each of those patterns. So there's really not too much going on here. It's just a matter of dropping in the values and throwing them at your calculator just to create a picture of what we have. They're providing us an angle A of 102 degrees. Again, opposite angle A is side little a, so that's a side we don't know. Opposite angle B is side B. They're providing that for us as 52 meters. And opposite angle C is side little c, and that's the 90 meters. All right, so notice we do have that side angle side pattern. We have those two sides with the angle between. So we can proceed with this formula. Here we go. Area equals 1/2 times the 52 times the 90 times the sine of angle A, 102. All right. And that's about all there is to it. We're just going to throw that at our calculator and get our result. So 2288.87. And don't forget the units, meters squared in that case. So on the homework assignment tonight, you'll see a couple of problems with this, but that's not the only thing. There will be a couple of problems where you are solving the triangle, much like what we had done with the previous section of notes. And then there will be a couple of problems for story problems. Sometimes they give us diagrams, and for the cases where they don't, that's what we're going to take a look at right here. How do we create this? In order to create a triangle that doesn't have, it may not have a base and a height in the way we've typically seen, a perpendicular base and a height, we're going to need to be able to place the angles that they provide us with respect to a particular reference line. So we're still going to be using a horizontal reference line in many of these angles, but there's some additional angle pairs that we want to review just to remind ourselves how to transfer the numbers around the picture. So you might remember if you have two intersecting lines, vertical angles are across that point of intersection. Vertical angles are congruent. And so that's going to be used in our diagram today. If you have parallel lines crossed by a transversal, corresponding angles are congruent. All right, so corresponding angles are the same relative position with respect to the point of origin. So here, if you think of this as sort of going up and to the right, we've got to the same location. If you go up and to the left, that would be another pair of corresponding angles. And then thirdly, if you have parallel lines cut by a transversal, alternate interior angles means that one has to be on the right side of the transversal, one has to be on the left side of the transversal, and interior means in between the two parallel lines. So we'll be seeing these in our diagram here. So let's read this through and then we'll break it down and then we'll focus on drawing that sketch. So we're talking about the lawn seating at a baseball field. It forms a 35-degree angle with the horizontal. See, there's your horizontal reference line so that we can create that angle. A vertically positioned flagpole is in the lawn seating area, and it casts a 42-foot shadow up the hill when the sun is at a 22-degree angle with the horizontal. So again, there's another reference line. And our goal is to find the flagpole's height. All right, so if you think about the baseball field, we would presume that's going to be horizontal. And that's really not part of our diagram, but that's just to get us started. So there's the baseball field. maybe there's a fence there, but at some point you have a banked area where spectators can come. They can bring their picnic blanket and just throw it down there and sit on the lawn. So this is our horizontal reference line. It says the lawn seating area forms a 35-degree angle with the horizontal. So right there is your 35-degree angle with the horizontal. Now somewhere on that we have the flagpole, so a vertically positioned flagpole. So vertically means vertical with respect to the horizontal reference line that we're using. We're not talking about perpendicular to the seating area. We mean vertical, that's in straight up and down. A vertically positioned flagpole casts a 42-foot shadow up the hill when the sun is at a 22-degree angle with the horizontal. That's a lot of information there. So where does the flagpole go? Here or here? We're not really sure, so we'll just pick a spot and say, that's my flag. There it is. We do want to find the flagpole's height, so I'll go ahead and put an H on that side. Now we have something about a shadow and we have something about a sun, so before we put those numbers down, let's think about two possibilities here. We're trying to create our triangle, of course, and the flagpole will be one side of the triangle because that's what we're trying to find. And the lawn seating area will be another part of the triangle. The question is, are we going to draw the third side of the triangle here on the left side or here on the right side? That's what we have to think about. So here's my sun. I'm putting that on tracing paper. We can move it around so we can figure out where the shadow is going to get cast because we're casting a shadow. If I put the sun here on the right side of the flagpole, then that means its beam of light would hit the top of the flagpole and it would cast its shadow on the left side down the hill. And we don't want that because it says we want this 42-foot shadow to go up the hill. So that means our sun has to be positioned here on the left-hand side so that when it hits the tip of the flagpole, that beam of light is casting a shadow. The shadow will go here, and that will be going up the hill. So by up the hill, we mean from the base of the flagpole and up. So there's your 42-foot shadow. So in other words, our sun is up here. If we draw a ray of light hitting the tip of the flagpole, for example, there's the third side of the triangle. And there's the shadow on the lawn seating area so that we know what each of these sides are representing. So the flagpole is a physical object for the left side of the triangle. The shadow and the lawn seating is the physical object for the right side of the triangle. The sort of upper right side of the triangle is top side. There's no physical object there. That's just representing this beam of light that is hitting the edge of the flagpole and is creating the tip of the shadow. Now, if we're trying to find height, and we're using the law of sines, and that means we need its opposite angle. So that's the next part of the puzzle. How do we figure out the angles on the inside of the triangle when right now we just have angles on the outside of the triangle? One of the angles on the outside of the triangle is this 35-degree angle. But we have another one here, this 22-degree angle. That's the sun is at a 22-degree angle with the horizontal. That means we need another horizontal reference line. So I'm going to put that horizontal reference line right here through the sun. And that's where we know the 22 degrees goes because it has to be touching that horizontal reference line and it has to be touching the thing that is going to cause the shadow. All right. So now let's bring in some of these other angle pairs. I'm going to draw another horizontal reference line through the right vertex of the triangle. And what we're looking at here is a pair of parallel lines. They're both horizontals. So these are my horizontal lines. This is my transversal. The lawn seating area is the transversal, which means that this 35-degree angle here is also found here because those are corresponding angles. Next, we're going to use the vertical angle pair because we want to get to that angle to the inside. So if this is 35 degrees, then that means this angle below the green horizontal reference line is 35 degrees as well. So again, be careful. The whole angle is not 35. It's only the 35 underneath that green horizontal reference line. Next, we're going to be taking a look at the reference line that goes through the sun. And again, this horizontal green reference line that goes through the right vertex. Those are my parallel lines. This is my transversal. So the 22-degree angle here will also be found here. These are alternate interior angles because one is above the transversal, the sunbeam, one is below the transversal, and they are in between or inside those horizontal lines. So add those up to get a grand total of 57 degrees. Next, let's work down here. Again, I have this horizontal reference line, which means this is, we could also draw the horizontal reference line right here, so those are parallel lines. So this 35-degree angle also is found here. Those are corresponding angles, they're congruent. And now we'll use a complementary pair because, hey, this is vertical, horizontal, they add up to 90. So that means we have 55 degrees on the inside of the triangle at the base of the flagpole. So we've got 2 out of 3. So now we could add them up to 180 degrees to find the third and remaining angle, and that's going to be 68 degrees. So that's the bulk of the problem right there, just trying to figure out how to transfer the information regarding the angles that are outside the triangle into the triangle using those angle pairs. Now we can solve using our law of sines. So the height over the sine of its opposite angle, 57, is equal to, there's the 42-foot shadow over the sine of its opposite angle, 68 degrees. All right, that's our problem. We'll multiply both sides by the sine of 57, and then we'll throw that at the calculator. So 37.99, and that's in feet.